she. If I change the block, I get to change the block. No, but actually, while Rafael is setting up, so in the context in the spirit of stories, no, that's mine. That you need that. So 2002, I think. I go to a crypto conference.
This is being recorded, right?
Yeah. Okay. So, okay, I can tell. Okay. I go to a crypto conference, and then we tell and we say, okay, might be Johan Hastad comes also. So why don't we go for a 3-day hiking in the mountains before crypto? So we plan, we do the reservation, we do stuff, and then Johan comes down from the airport for the airplane. We wait for him in LA, and this young guy comes with him and says, I brought my student with me. I hope you don't mind. Great. So then we come, and then this student read this UC paper, and it starts bugging me for the whole 3-day trip about things that don't work, and this global state and stuff, and that was him, and he ruined the whole 3 days. Ruined the whole 3 days, and and you don't understand that, and then I couldn't enjoy the 3 days, but the worst part of it is that he was right, but then there were papers written left several years after that. But anyway.
Thank you, Ran. It was I thought you were talking about a different story on the same trip there, in the parking lot and the bar, but that was okay. So I'm going to talk about consensus through herding, and this is a joint work with Hubert Chen and Lane Shi. So let me briefly review what we're talking about. You all know what consensus is now, but just to make sure we have the same terminology. So we have a set of nodes. They would like to agree on an ever-growing set of transactions, aka ledger. And we require two properties: consistency, meaning that any of these two nodes roughly should see the same view of the ledger. And liveness means that whenever somebody wants to add some transaction, it should be added and also sufficiently fast. So as you all know by now at this point of the workshop, consensus has lots of different names. What I mean by, or lots of different meanings, but what I mean by it is just state machine replication, and what's today is more commonly known in the blockchain community as a permissioned blockchain. But really is all the same thing. All right, so a little bit more precisely, let's go over these two properties of consistency and liveness. So we said these nodes would like to agree on this ever-growing list of transactions, also known as a ledger, right? And consistency says two things. The first thing is that at any given point, if I look at any two nodes, it should be the case that either my ledger is a prefix of yours or vice versa. Right? That's what it means that we agree. Maybe you have seen some more transactions. I haven't caught up yet, but at least whatever I have is a prefix of yours. But presumably I will catch up very shortly. And the second thing, which is also very important, is that actually I am consistent with myself in the future. So my current ledger is always a prefix of my ledger in the future. So whatever I've written there should always remain. So that's consistency. And liveness says that whenever some honest guy sees some transaction, either because he gets it as an input or he sees it from somebody else, it should appear in his ledger sufficiently soon. Okay. So in particular, if you and I have some disagreement, your ledger is longer than mine, that means that eventually it will get added to my ledger also.
Okay. So how did that definition deal if I send conflicting transactions to two different honest players?
Okay, so right now, I'm not talking about transaction as a Bitcoin. This is just like some messages. In that case, these things will always get added. You can always, on top of this, like, prune things that are invalid in some sense. But this is just like a way to, a ledger of messages, everything is considered valid. It's just the easiest abstraction to talk about. So this notion of liveness I consider here, that says that whenever somebody sees something, it should get added to the ledger sufficiently soon. is a very strong notion of liveness. And to achieve it, you need to consider a synchronous model of computation, because otherwise, if message can be delayed forever, you can never hope to make sure that everybody sees that transaction. So we're going to be working in this synchronous model of communication. In particular, I'm going to talk about a model called the Diffusion Model, where the protocol is going to proceed in some fixed rounds, fixed time steps, just like in a synchronous case. And whenever somebody wants to send a message, they're going to diffuse it over the network, and it will arrive at everybody within some fixed delta time. This is an upper bound on the time it takes for the message to arrive. So by now, you're pretty used to this model. You've seen it in lots of talks yesterday. This is the model that Bitcoin is analyzed in. And we're going to be using the same model. Another thing that's important to note, that we're going to consider a model where all messages are authenticated. So whenever you send something, I know who it's coming from.
Rafael, when the adversary sends something, is it guaranteed to arrive to?
Yes. So here we're assuming that even if no matter who sends it, good guy or adversary, it always arrives within delta. So you can relax the model to assume it only holds for honest players, but it does lots of generality because you can always add some echo protocols to ensure that it arrives at that also when the bad guy does it.
Instead of authenticated, if I think point to point,
yeah,
will be okay.
Well, point to point also requires authentication. If you need to know who it comes when you point to point.
No,
yeah.
Point to point means that when
point to point with authentication.
I know the
yes,
line is
sure, yeah. But right now, I'm going to talk about communication.
Authenticated is a very complex word, so I'm trying to replace. You mean point to point? That's it.
I don't mean point to point because I'm going to be talking about communication efficiency. That's going to be the main thing I'm going to be talking about. And so I'm interested in how many messages I need to send on this diffusion channel. So I'm sending a message that gets sent out to everybody.
But you mean the messages have a source?
Yes. So the protocols I will be discussing later on is going to use a PKI, so we have signatures. So really, whenever you send a message, you know who it comes from.
Shouldn't you add to this allow malicious users to have private communication channel for themselves?
You can. I'm just saying, like, this is the cleanest model. This is the way Bitcoin is. You can add it to it. I'm going to be only focusing on this simplest case. Okay? So.
Do you assuming rushing adversary that they can look at my message?
The attacker is, I'm going to consider an attacker that, yes, he sees the messages and he can actually control the scheduling of the messages. So, and he can delay it by delta. So the attacker is controlling the network. Whenever you want to send a message, he decides when to deliver it within delta steps. Very good point. Thank you. All right. So just to make sure that we understand this consistency and liveness in this scenario, just like Ran talked about, the reason we really care about, or today about consensus and these two properties is that any consensus protocol really allows us to implement a global public ledger. So really think of this as having some Facebook wall, let's say, where you can post messages, and everybody who wants to look at this thing will see a consistent view. It won't be fully consistent, but it will be consistent with plus minus some delta time. So what I mean by that is think of having this idle functionality where whenever somebody wants to add a message, it will get written to it within delta time. And whenever somebody wants to read it, you will see what's currently written there plus minus time delta. All right, so maybe Ran us to look at it, and he will see what's written up till time 11 and 27, and Dahlia looks and she will get 11:28, but it's very close to what's written there.
So there's no total order, so we don't agree on the sequence?
So we will agree on the sequence, but we also have, it really is like, I'm looking at the sky, this thing has been written in the sky, but we might see slightly different angles, but so it's plus minus this little delta time in how things are.
Right? There is
a fully written thing on it, but we might see like what was written at different times, plus minus delta. So in particular, if you wait another 5 minutes, you will get to see what he saw for sure.
It's just prefixes of the same.
Yes, but it's a little bit stronger than just prefixes, because I also know that if I see something at 11:28, when you look at it 11:30, you will also have seen it, because it's right. So that's what these two things give you. So it's a very strong strong and natural thing. All right, so what's known in this classical model? Well, all these classical results that you've heard about already in bootcamp and probably today. So we can achieve consensus assuming less than 1/3 being corrupt, and that's also necessary. And in the PKI model, if you also have a setup where everybody has a public and secret key, you can actually achieve even up to n-1 corruption. So you can do much better. And additionally, in this PKI model, you can achieve something that has a very nice liveness property that transactions actually get confirmed in expected constant number of rounds if you go up to n/2 corrupted players. Okay, so that's in the kind of classic results from starting from the 80s. And let me kind of go over the high-level approach that this type of consensus protocol are constructed, because it's going to be useful for me later on. And it's a very, very simple recipe. So we're going to proceed in rounds or in epochs. In each epoch, we're going to pick some leader. This leader is going to bundle together a bunch of transactions into a block. Okay, and then he's going to send out this block to everybody. And then we're going to run what's called Byzantine Agreement Protocol or multi-value agreement protocol in order to agree on this block that we saw the same thing. Okay, if we run this agreement protocol and we saw the same thing, then we can make sure that we add this block to the ledger, and we're all done. Yeah.
You see a lot of details and definitions, but I don't understand, where are you going?
Well, we'll get there soon, okay? If you don't interrupt me, maybe I'll get there. All right, so what is a Byzantine Agreement Protocol? You've seen it before also. Let me go over it again. So in a Byzantine Agreement Protocol, we have a set of players, and you can really think of it as a single-shot consensus. Okay, so we have these players. They all have some inputs, and they're going to run some protocol and eventually produce an output. What we require is that any two honest guys should get the same output. That's what agreement says. So run this protocol. Any two honest guys should really always get the same output. The protocol should terminate fast. And eventually, what we also want is this non-triviality property, that if everybody starts off having the same input, then that is the output they should get. If all the good guys start off having the same input, then they also should produce that output. So if we go back to this consensus construction from a BA protocol, if the leader proposes a block and sends the same block to everybody, then when they run the Byzantine Agreement Protocol, they indeed all have the same input, and therefore they will confirm that block and get that as an output. Okay? So if we have a Byzantine Agreement Protocol, then we directly get the consensus protocol using this simple approach. Okay? So we just go in different rounds. We have different leaders in every round. The leader prepares a block, sends it out to everybody, and then we run Byzantine Agreement to make sure he indeed was honest and sent out the same block to everybody. All right, so now to the topic of this talk. So in today's world, we'd like to run this consensus protocol in a large-scale setting. Right? So Bitcoin enabled running consensus among millions of nodes. And in order to do this, we need to have a protocol, theoretically speaking, that scales well with the number of players. And what I mean by scale well, I want it to scale polylogarithmically with the number of players. And the original protocols don't do that. In fact, they grow linearly. The communication complexity is linear in the number of players. But Nakamoto's blockchain protocol actually does. It's the first protocol for consensus that scales polylogarithmically with the number of players. So that's an awesome feature. But of course, it relies on proof of work, and which is not desirable for many different reasons. Okay? So
it doesn't solve the consensus specification you gave us.
It doesn't solve what?
The consensus specification you gave us.
No, it does. It does. I'll discuss it later on. Nakamoto's protocol does indeed solve this problem. Exactly. So let me go over a little bit more formally what I mean by communication efficient protocols. So I want a protocol that satisfies two properties. The first one is that the total number of bits that I'm sending on this diffusion channel should be small. In particular, it should grow polylogarithmically in the number of players and linearly in the length of transactions and the security parameter. Okay? So if you want to confirm a log of 1,000,000 transactions, you want this communication complexity to be 1,000,000 times polylogarithmic number of players. And the second thing that you want is that whenever you want to confirm some transaction, it should get confirmed in time that's polylogarithmic in number of players also. You can't afford to wait for 1 billion runs or 1,000,000 runs if you have 1,000,000 players. Okay? These two properties make sense? So that's the notion of communication efficiency that we're after. And indeed, Nakamoto's protocol satisfies this. So now the first thing you might ask is actually, sure, the original protocols don't satisfy it, but really there should be a trivial way to make them satisfy it. Right? Why don't we just simply sub-select a small committee among all the nodes, a committee of size polylog n? The fraction of good nodes is going to actually remain roughly the same by a Chernoff band. And then we just run the protocol among those that committee. So what's wrong with this? Yeah.
I think a lot of committees in infinite ledger.
It's a lot of.
Any chart of bounds is.
Okay, sure. The chart part is tight. Okay, that yeah. So I'm not so worried about this. Is in theory. All of this is going to be in theory now. So that is not the issue I have. Yeah.
This is not the interruption answering.
Sorry. No. Sorry. Yeah, answering yes. This. Yeah. Sorry. Yeah. Go ahead. Yeah.
I mean, selecting committee itself is a problem.
Selecting committee itself is not trivial, but if you have some setup, if you have some kind of common reference string.
The consensus is selecting the leader, that's all.
Sure, but like selecting a committee, it says maybe you do it once and for all, it's not so bad, yeah?
Polylog n is much smaller than 1/3, right?
Yeah.
The adversary could corrupt it.
So yeah, so this is the issue that like once you know who the committee is, it's very easy for the attacker to just corrupt the whole committee. And polylog n is a very small number. So if I know if it's you 5 guys doing this thing, I just corrupt you guys. Now it is true. This works if you consider a static attacker that decides who to corrupt ahead of time before the committee is selected. But once if the attacker can corrupt people after knowing who the committee is, then you're dead. So that's why this approach doesn't work. Okay. So really, to make this question non-trivial, we need to consider also adaptive security. Right, so we want a communication efficient protocol that also is secure, that satisfies consistency and liveness, even when attacker can adaptively corrupt the players throughout the execution. So he sees message, protocol is running, and then he sees who's in the committee, and he gets to corrupt them at that point also.
So it has to do with the complexity of selecting the committee, because of course, I will select committee, will select, I'll go on, I mean, I'll select committees from round to round.
We'll discuss Algorand very shortly, because Algorand is a way to try to overcome this. Yeah.
The issue is the committee, selecting the committee.
It's how to select the committee in order to make it very hard to corrupt it, yeah. Okay, so the main question we're discussing today is, can we achieve communication efficient consensus with adaptive security? Right, so that's the main problem. And before I tell you what's known about this thing, let me just point out that one could also discuss the related problem of just getting Byzantine agreement, which was a single shot consensus. And in fact, that has actually recently been solved. So there are protocols that are communication efficient and adaptively secure for Byzantine agreement. And now you might ask yourself, okay, if we solve Byzantine agreement, it should be trivial to go to consensus. We saw this previous recipe, right? Just do this epoch-based thing, leader sends something else, run Byzantine agreement. The point is that recipe actually does not preserve, well, it preserves either efficiency or adaptive security, but doesn't preserve both. Right? If you select the leaders at random, Then once I know that you're the leader, I can corrupt you and mess things up. So it's not going to be adaptive secure. If you do some kind of round robin based things, then you actually preserve adaptive security, but it's not going to have it's not going to be communication efficient because you need to iterate through a lot of leaders.
And again, the Bitcoin gets rounded because
We'll get to Bitcoin in this slide here. Okay. All right. So what's known about this so far? Okay. So remember, we're all talking about communication efficiency and adaptive security. So the first result to achieve both of those things was Nakamoto's protocol, and one could analyze it and show that indeed it satisfies adaptive security also. Nakamoto's protocol trivially satisfies communication efficiency, but also the analysis that you heard some about yesterday indeed actually shows also this strong form of adaptive security. Okay. And even if you set the parameters correctly, even if the attacker controls the left and half of the guys. Okay, so that's the first result. But we said it reuses proof of work, and then we had the beautiful Algorand result that came along by Chen-Mi Kali, and they also managed to achieve communication efficiency and adaptive security. This time without proof of work, so they achieve a consensus protocol in the setting that we're interested in. But their protocol relied on a strong feature of the computational model, something called erasures. Okay? So they show a protocol if you assume that honest players can erase state perfectly. Okay. And I'll discuss a little bit more what this erasure means. But it's the erasure model. It's well understood in the crypto community. It's actually very it's a hard abstraction to obtain. It's not easy to erase your state in a way that is impossible to recover. So ideally, we would like to have a protocol in the standard model where we don't make any of these like kind of trusted assumptions. Okay, and that's the goal with our work. But before I go to our work and how we achieve this, let me explain how either proof of work or erasures overcome this issue that we had with subselection, because it's very instructive to see what problem it's dealing with. So the first problem we had with subselection, of subselecting a committee, is that it's important to make sure that I cannot a priori predict who's going to be on the committee, right? If I know you're going to be the leader in round 10, I should just corrupt you, right? So it's very important. I cannot predict who is going to be the leader to speak. And with proof of works, like Ran was asking, nobody knows who's going to be elected leader, right? In proof of work, the way you elect leaders is you're asking people to find some puzzle solution, and a puzzle solution is some data such that a random oracle applied to the current chain, and the new block in the puzzle is something smaller than D, right? So everybody tries to find this puzzle solution, and nobody knows who's going to find it, right? It's completely random, and attacker has no clue if it's going to be you, or you, right? So a priori predicting is not possible. Okay. So that's a great feature of this type of proof of work-based schemes. Now, how did Algorand and Chen-Mi Kali get around this thing? It's a very clever idea of using something called a verifiable random function. So what's a verifiable random function? It's a pseudo-random function that has the property that only the person who has the secret key actually can evaluate it. But once I evaluated it, anybody can check that the answer is correct. Okay. So think of it as a private way to evaluating kind of a random oracle, but that later on can be verified. Now, what they did was more or less trying to kind of replace the random oracle here with a VRF. And I'm going to do this leader-based leader election, where I'm going to say that you are a leader in some round J. If when you apply the VRF to the round number J, it becomes smaller than some difficulty. So I'm going to elect you leader at random if when you apply the VRF to the round number, you get some good result. Okay? And note that only you can do this. So you can predict in what rounds you're going to be the leader, but nobody else can do it. Okay? So this is a great way for overcoming this a priori prediction problem. Everybody knows on their own when they're going to be leaders, but and then later on when they're leader, they can present this evidence of it because they give the output, and everybody can check that indeed they are a leader. But we don't know ahead of time who's going to be the leader. All right, so this is great. This prevents this simpler type of attack of like a priori predicting who's going to be leader and corrupting them. But we have a more serious attack actually, which is that when the leader has spoken, why don't I just corrupt him after that, right? Like when you send a message, then I know for sure you were on the committee. So in some sense, I need to be able to also have to prevent the fact that I can a posteriori corrupt somebody. And that seems much harder. Now let's see how that is overcome in these two solutions. So actually with proof of work, just the fact that you were the leader, you spoke, if I corrupt you after the fact, doesn't help me at all. And the point here is that just because you mine a block is not going to make you more likely to mine the next block, right? You're lucky now, but that doesn't mean you're going to be more lucky. And it relies on the fact that this election of who is leader is tied to the actual message you're sending, right? It's tied to the block you're sending. Whether you're elected leader depends on that particular message. Okay. Now, how do you do it with VRFs? Now it's more tricky because once you've been selected leader, then you're the leader, right? It's not. It was only based on the run number, and this is how. So the way Charlie and Michele get around this thing is by using erasures. They say, before I'm going to send the message, I'm actually going to delete my secret key. Okay, so I was elected leader, great, I'm king, but I produced the message I'm going to send. But before sending it, let me also erase all my secret keys that were needed to create this message. Okay. And then I'm going to use something called a forward secure signature scheme that makes sure that I will be able to sign things in the future, but not things in the past. And since I erased the key for the past, if someone comes and corrupts me after I sent the message, I don't have anything that allows me to be more powerful than anybody else. So it's a very elegant idea of saying, look, let's just erase the thing that made me king, and then if someone corrupts me after I'm speaking, I'm no longer king, right? They don't have the keys anymore. Okay. So, now, as I mentioned, the problem with erasures is not easy to do it always. There is also a problem with this that has been pointed out in literature previously, is that also it's not clear why people actually should erase it, because if keeping this key is valuable because an attacker can corrupt you and make use of you, why should I erase it? It's actually worth something for me. So maybe I'm stupid to erase it, right? So an honest, like an incentive-driven guy maybe shouldn't even erase it. So the question is, how do we remove these erasures? Okay, and the natural approach would be to say, look, we learned something from Bitcoin. Right, what made Bitcoin work here was that actually who was elected was tied to the message. Right? I applied the random oracle to the actual message I'm sending. And that was the key to make sure that whenever I send something, if I want to send something else, that doesn't, corrupting you after you send something doesn't make you more likely to be allowed to send something else. So can we do it here? Why don't we just apply the VRF not only to the round number, but also to the message I want to send? Anyone? Grinding, exactly. Right? There is actually a reason why Bitcoin relies on this assumption of that computational work is limited. Right? If I apply the VRF not only to the run number, but also to the message, an attacker could try lots of different messages and get a much higher probability of getting elected. Whereas the good guys, they only try one thing. The bad guy can try lots of different messages.
Can you repeat this grinding?
So if I apply the VRF, not just to the run number, but also to the message, the good guys, in each round, they will apply it once. But the attacker, he can try lots of different messages. He can maybe re-randomize his thing and therefore get...
Have the whatever guy commit to the message, but not have the thing depend on it as a probability of success. Just has to commit to a message, and then then you decide.
That might be an approach. I'm not sure how to make that work because, like, how do you? I don't know. We can say, yeah, but
key that you use. You can try different keys until.
Different keys you cannot try because you only have one secret key. Like you have VRF for all you.
Can I try until I get?
No, so you have the VRF commits like the VRF, the public key commits you to a single secret key. So the VRF is deterministic. That is the property of the VRF. You cannot apply the VRF to. You cannot get many different outputs for the VRF. That's indeed the crucial security property of VRF.
Can I also ask? So I missed the beginning of the talk, but in the previous
Big problem. Yeah.
In leader selection, you are only selecting one guy, right? Can you go back? I was expecting the audience to ask, but nobody asked, so I have to skip.
Sure.
Are all this only has one leader selected?
Yeah. So here you can, if you're unlucky, you can select.
What if the leader just leaves the system?
No, if the leader leaves the system, then it's like he's a bad leader, and eventually find another one that's good.
So
Right. That's like it relies on.
for that type.
Yes, sure, exactly, yeah. So this is we're going to keep picking leaders until we get someone who's good, and then the broker is created. Yeah. Thanks for the question. All right. Okay. So our main result, I don't have that much time, is that we can actually achieve communication efficiency without erasures. Okay. Under standard assumptions. In fact, we don't even use random oracles. We use a public key and a common reference string. So assume there is a random string that's not selected. And standard cryptographic assumptions with sub-exponential security. In type minutes, I might explain why we need sub-exponential security. But the key point here is no erasures and no proof of work. Yeah.
So I presume you need to limit the adaptivity. So you're assuming that the adversary can very quickly attack your keys and penetrate you, but not block the dissemination of your message.
No, yes. So after I have sent out a message, that's a very good point. I will talk about at the end. But the model we're considering, because we have that paper showing a lower bound, that you have to, after a good guy has sent a message, if the attacker corrupts him, he cannot withdraw that message that has been sent.
So in some sense, the open question that remains after all this great work is, can you do a sub-quadratic Byzantine agreement against a fully adaptive adversary?
No, because there is a lower bound, right?
No, we cannot.
No.
Yeah.
Not even at the point-to-point channel. The diffusion is, no.
We'll discuss it later, but yeah. Okay, so I probably won't have that much time to go over the whole approach, but at least let me go over the high level. So the high level of the approach is to, in fact, define a new notion of a single-shot consensus that's stronger than Byzantine agreement. We said Byzantine agreement didn't quite work well to compose like this with leaders. So instead, we define something called a batch agreement protocol. And this notion of batch agreement protocol will actually turn out to compose very nicely. And that will be very easy to compose nicely. And then the key thing is to construct this batch agreement protocol from something called herding. And I'll describe what herding is. It's a beautiful, I'll describe shortly what it is. Okay? The key point here is that using herding in order to construct this type of consensus protocol is something that will allow us to use actually this message-based election. We'll be able to allow using a VRF applied to not just the round number, but also the message without suffering these grinding attacks.
Who's B92, Rafael?
Sorry? B92, I'll talk about that shortly. This is a guy called Banerjee, who just got the Nobel Prize last week. So it's an economist. And this was his probably most celebrated work on herding. So I'll tell you about this Nobel Prize work very shortly.
That's just a main question. The reason the message have the problem, is it plain text attack? Because everybody knows the message and they can try it. Is that the nature of weakness?
With this grinding thing, when everybody knows the Yes, the problem with this, when you tie it to the message, is that people can just try many different messages to make sure that they get collected with greater probability.
Because you see the messages, or?
No, because like, if I'm trying to get on the committee, let's say that I'm supposed to send some signature on something, I can just try many different, change one bit here and there, and just to make sure I get elected on large.
With the VRF,
yeah.
If the adversary gets on you, and now, I don't know, you have secrets or whatever, so in later rounds, if you become leader, it will be able to corrupt you.
We're talking about Algorand or?
With the VRF,
yeah.
I don't know, Algorand, the VRF. The VRF is essentially you have a secret, and if somebody knows your secret, can imitate you or not.
If somebody knows your secret VRF, yes, they can imitate you. Yeah, but the point that when you get corrupted in a particular round, right, it doesn't make you more likely to be elected leader in other rounds in the future than anybody else.
In the proof of stake, it means you have a lot of money, and the probability that you will be a leader again, it's pretty high.
So right now I'm not in any proof of stake setting. It's just a normal. Okay, so another thing I want to point out there is we assume only 1/3 are corrupted, similar to Algorand.
So over here, can you replace the batch agreement by a standard visiting agreement definition?
No, so I'll tell you what the batch agreement definition is now. It's very similar to standard business agreement with one little tweak. So batch agreement, now, thanks Ron for, I left, but he explained to you universal composability. So it's a definition that's kind of similar to that. So you have players. Players are going to be receiving some transactions from some environment. Transactions coming in over time to the players, okay? And they're creating their view of whatever transaction they see. At some point, the environment is going to say, start, and then they start running a protocol. And at the end of it, they produce some output. So the first property of agreement is just as before. Everybody on it should agree on the output. Second thing, termination is just as before. It should terminate fast. And now there's a validity requirement, which is slightly different. Remember, validity said before that if everybody had the same input, then you output the same thing. Now I'm going to have a much stronger validity requirement. This validity requirement says that all the transactions that were received long before the beginning of the protocol, long before the start message was sent. So in particular, what I call T0 minus delay, where delay is some fixed time. They should always be included in the output. So any transaction that everybody saw long ago must be included in the output. Yeah?
I have a question about the threshold. Is 1/3, is there a lower bound?
No, we'll discuss it towards the end. It's still open to get 1/2. We think one should be able to do it, but it becomes much more messy, so we kind of didn't do it yet.
This definition sounds similar to interactive consistency, right?
I'm not quite sure exactly what the relationship is, but look, it seems very likely that maybe something like this has been considered before. It's a very natural definition. Just says whatever you have received up until long before the beginning of the protocol, everybody needs to include it. Okay.
What is the difference between batch and the ledger? In the batch,
this is a single. This is a single shot thing. This is just.
Shot is nothing. I mean,
okay.
What is the meaning of a batch?
A batch is a block of transaction. A batch is.
If you say that what I have and what you have is only different by delta, it starts to be.
It's almost the same. That's what, like the next slide says.
One is set and one is a sequence.
That's exactly the difference. Once you have batch agreement, you can get consensus trivially. You just run batch agreement 1, and then once you're done with that, you run a second batch agreement, and you just run it sequentially. That's the only thing. A consensus protocol.
Computing consensus always been one thing, not, I mean, this.
Okay, we can agree to disagree, it doesn't matter.
One by one.
Replace my consensus with whatever, yeah.
So in the validity, this guarantee that you have the T minus T0 minus delay will ensure that the message is on the network by the time the...
Exactly, yeah, exactly. So the reason we want something like this is that when a good guy sees something, all the good guys will have seen it within delay time, and therefore they will all have it, and they should include it, yeah. And so this is really why this, once you have this single shot thing, can trivially get consensus. We could just run the protocol to agree on one block, then run the next one, and so on and so forth. And that's
transactions which are double spending. I may not right now know about it, and somebody else may know about it.
So we're not talking about transactions here just as a ledger of messages, okay? Yes. All right. So now let me get you to herding. Herding is this very beautiful phenomena that was observed in the economic literature by this economist called Abhijit Banerjee, who, as I said, he just got the Nobel Prize last week. And what he was considering, this was actually during his PhD, he wrote this work. He's looked at the following problem. So we all get some beliefs about some event. So let's say, does smoking cause cancer is some event, W. And let's say we all get some independent signals about this event. And let's assume that all these signals are equally strong. Okay? So everybody gets some belief, BI. This is the signal. And I know that BI equals to the true state of the world with probability, let's say, 3/4, 1/2 plus epsilon. Okay? Now, we do know that if everybody just announced their guesses and then we took the average, we would get a very, very good prediction of what the true state of the world is. That's something known as the wisdom of the crowds, right? So it's great if everybody announces at the same time. We'll be able to determine the true state of the world very, very well. But then he said the following. In the real world, that's not how things go. People instead announce their opinion one after another often, right? So we're going to consider a game where I'm going to announce my belief, and my utility is high if I make a correct guess, and low if I make an incorrect guess. So I would like to guess correctly the true state of the world. And then Eli goes, and then Stefan goes, and so on and so forth. Okay, and everybody sees what everybody else did before. All right. So what should we do first? Okay, let's say Stefan starts. What should he do? He should clearly output his guess, right? He doesn't have any other information. He should guess whatever his belief was, BI. So guess 1 equals to B1. All right. Then Eli goes. Okay, what should Eli do? He's seen his own belief, B2. He's also seen Stefan's guess, G1. Okay? But, these are the 2 bits of information. He might as well trust his own thing more than Stefan's. So he's going to value his own belief stronger, and therefore he's also going to output his guess, his belief. So guess 2 is going to be equal to B2. Okay? This actually requires a little bit of an argument. It requires relying on the fact that Eli thinks that Stefan is rational, but the right thing to do is, of course, just output your own bit. Now, let's say I'm the third one. What should I do? Let's say that both Eli and Stefan actually said 0. They don't believe smoking causes cancer. Okay? Me, on the other hand, the evidence I've seen, the articles I've seen, say that smoking does cause cancer. Okay, what should I do?
If I want to win, I'll say 0 too.
If I want to win, if I believe that you guys are rational, then under that assumption, I also believe that your bits were 0. So your signals were 0. So therefore, if these signals are independent, the way I view it is, look, I have seen 3 signals. 2 go for 0, 1 go for 1. Easy. I should go with 0. So my signal actually is completely uninformative at this point. Right? And what about the next guy? Same thing. He does 0 also. And so everybody else continues doing 0. And we get something called an information cascade. Even though we had this very strong signal, everybody just says 0, 0, 0, 0, 0. So this has more recently been used to describe the spread of fake news. Even if I know better, if lots of my friends are like posting an article, I'm going to post that also because I think that they must know something I don't know. and then I just copy that thing, and then we just get crazy things spreading in social networks. Has lots of very important and interesting consequences. Okay, and what's also very important here to note is that these cascades actually happen with very high probability. In fact, probability almost with probability 1, these cascades will happen. Okay, and with probability 1/2, we'll cascade on the wrong thing. Not 1/2. Well, with high probability, we'll cascade on the wrong thing. So that's terrible, you would think, and you get something, what's could be called the foolishness of crowds. Even though we have strong signals, we still all say the wrong thing. Okay. So a little bit more precisely, what you can show then is like if you assume common knowledge rationality, that everybody's rational, everybody knows that everybody knows that everybody knows that everybody's rational, then the right thing to do is that I'm going to guess the most popular bit that I've seen so far by combining my initial belief and the number of votes I've seen. So what I should do is I look at my initial belief, I'm going to evaluate something, and I see how many votes the other two bits have, and I'm going to look at what's most popular, combining the two. And I'm going to do that. And then you see, of course, that like once you have a majority for one, it's just going to continue cascading on. So that's terrible, but for us, that's great. Because we're trying to achieve consensus, we don't care about truth or false here. We just care about agreeing, right? So for us, that's all we want. So let me explain how we get a batch agreeing protocol using this herding approach. And the idea is actually, yeah.
Because you're using herding, do you have to assume that the committee is fully rational for correct?
No. Yeah, this was just, herding uses rationality. We're going to assume Byzantine attackers, right? But we're going to use the herding protocol, and we're going to show that herding is actually robust also for Byzantine attackers. And not only that, it will also get you this nice adaptive property. All right, so.
You are now also over.
I am, yes. So I'll finish in. So I started the. Oh yeah, okay, yes. I'll take 5 minutes and then, and then I have to run to my flight. So this is how the protocol will go. Just like in herding, everybody is going to score. They need to vote on transactions, right? And they're going to compute a score for each transaction, each block of transactions. And the way they compute the score is they have some initial score. Think of this as an initial belief for the transaction. And they're going to add on to it the number of votes that the transaction has received from other players. And that's going to be the actual score at the moment. And then in every round, if I'm elected leader, I'm going to be voting. And then I'm going to vote for the most popular transaction I've seen so far. Okay, so just like in the herding, I vote for the most popular choice if I'm allowed to vote. Now, so we're running the herding exactly as herding, except with these tweaks that we need to also decide what order to take the players. In herding, you have like people go one by one. So the way we're going to decide whether you are eligible to vote is we're going to use a similar trick to Algorand using a VRF. But now we're going to apply the VRF not only to the round number, but also to the transaction. So now we're going to use this transaction-based voting. So I look at the transaction and the round and apply the VRF. If that is small, then I'm allowed to vote.
Are the transactions a concatenation of the transactions proposed, or are they hashed down to a smaller implicit?
Very good. So for now, let's think of it as a concatenation. But indeed, in the actual proof, it's going to be important that you hash it down to something small. So maybe I'll time, maybe not. Okay, so the important thing here is we do this transaction-specific eligibility, and this is indeed what prevents this a posteriori corruption, right? So the fact that I can corrupt you now, that doesn't make you more likely to be allowed to vote on anything else, because vote eligibility is transaction-specific. Now, I haven't told you how to do this initial score, right?
Are you assuming everyone has the same TX set?
No, everybody sees different TX set, and then they're going to vote for, yeah.
So is it possible that somebody comes up with an ASIC that does VRF, that basically...
No. So you only run the VRF one. You're asking about this grinding thing. For some bizarre reason, this protocol actually is not, I'll discuss it very quickly at the end, but grinding cannot be done on this thing for some magical reasons, okay? But before doing that, let me just explain how to do the initial score, because that's the most interesting thing. So right now, what we said was we're combining some initial belief with the number of votes, but I didn't tell you how to form your initial belief. So how will I form my initial belief? I'm going to compute an age of a set of transactions. The age is the time since what is the latest transaction that I have seen that's not included in this block. Right? If this block is omitting some very old transaction, then I claim this is really it's a bad block, it's an old block. Okay? And the way I'm going to score things now is going to be something that is some constant that's exponentially decaying in terms of age. So blocks that have small age, they're very young, they contain all the transactions, they're going to get a high score. But if you're omitting a lot of transactions that I have seen, then I'm going to give you a very low score, and the decrease is very fast. Okay? And the reason, maybe what the actual function is doesn't really matter, but the two properties I want from this function is the following. Any two honest guys, the initial transactions that they have are going to be scored very similarly. In fact, for any set of transactions, any two honest guys will score them very, very closely because they have roughly the same age for honest guys. So that's important. Honest guys are consistent in the scoring. And the second thing is that the actual set of transactions that I have currently seen, I'm going to score it very high because it has age 0, contains everything, so I'm going to score it high. That's number one. But something that omits a lot of transactions, since this is exponentially decaying, it's going to be scored very low. So things that omit old transactions, things that the batch agreement should never output, is going to get a very low score. Okay. And now I don't have time to really go over the proof, but the key point here is that since everybody, good guys vote consistently, we'll make sure to have a lot of votes for something. Yet, things that have a bad score, a bad initial score, will never get votes from good guys. Good guys will never vote from any bad transactions because they have very small initial score. So even if you get many bad guys' votes on it, it will never bring it up to be high enough. So I do this very fast now. I'm sorry because I don't have time. But you can give a proof that this satisfies both validity and agreement, and it works. The proof is actually relies on this. The proof of this relies on this convergence opportunity proof that you heard discussed before, that we used to analyze Nakamoto's protocol, and you can just look more in the paper. Let me just, towards the end, just address this question of grinding. Okay? And it's going to be very high level now because I didn't cover the proof. But the point of this proof is that in the proof, we're going to be relying on Chernoff bounds a lot. And we'll show that certain things hold for a certain transaction with high probability over the Chernoff bound. Okay? So we'll show, in fact, that there is no, with high probability, there is no bad transaction that can compete with the one that's being output, that will get many votes.
Can you repeat that?
Okay, maybe let's say. So the way the argument goes is like, I'm going to say, like, let's assume for contradiction, there are two transactions that could get a lot of votes, Tx and Tx prime. And then I'm going to say that's not going to be possible because with high probability, the total number of votes you can get for both Tx and Tx prime is bounded by some 4/3 K. And at least one transaction is going to get 2/3 K, so both cannot get 2/3 K. Okay? So for any fixed set of transactions, I know with high probability, not both can win. Okay? And therefore, I'm going to conclude that one of them is, there's only one that can be output. Okay? Now, the issue here is you have this grinding that maybe I can find some transaction that's going to allow the attacker to get many votes. Right? Maybe the attacker can search for these transactions that allows him to get many, many vote opportunities. Now, we're going to be using the fact that actually these transactions get hashed down to something small. So the actual set of hashed down transactions is a small number of bits. Let's say K over 2 bits. But the Chernoff bound is going to be holding except with probability 2 to the minus K. So the Chernoff bound holds except with very, very high probability. Except with very, very high probability. Except with very, very small probability, the number of votes you can get on any transaction is going to be roughly 2/3 K. Okay? So even if you enumerate over all possible transactions, even if you could do grinding and go over all of them, you will not find one for which the Chernow band kind of fails. And that's the way you get around this grinding, that even with ASICs, whatever, doesn't matter. Even if you go over all transactions, it does not allow you to break this protocol. And I'm sorry this is vague because I didn't have time to go over the proof, but at least maybe it conveys an intuition of why grinding is prevented. Yeah.
So the solution to grinding is basically make the search space very small, such that you cannot like break the bound.
Yeah, exactly. Yeah, so basically it's going to be using kind of a union bound over all possible. Yeah.
How is polylog communication in total? I mean, you have polylog many people in the committee that need to prove to everyone, they don't know who the others are, right? So they need to...
No. So yeah, it's polylog communication in the diffusion model. This is exactly like in Bitcoin, right? It's polylog messages in the diffusion setting, yeah.
What is the role of common reference string in the construction?
Sorry, we're gonna...
The common reference string? It's... Thank you. So the common reference string is to select. It's after. It's a break. It's to select the VRF.